Welcome back. We have covered Q-learning using a simple grid world example, and we use Q-table for that. The code implementation and explanations are accessible in my free Udemy tutorial, Vehicle Suspension Control 4, PID Tuning with AI TD3. You can enroll in that tutorial for free, and the link is in the description. Also, note that the free coupons that I offer for that, they have limitations in terms of time and the number of enrollments. However, don't worry, I will be renewing them periodically. But now, it would also be interesting to convert this grid world problem to a neural network form. One way how this could be done is by having a neural network with two input neurons, one for each component of the state. This would be a row, and this would be a column in the grid world. Then we would also have some hidden layers, and then each output neuron gives you an estimate of the Q value for each action that you take considering that state. You would train the network to predict Q values for every action given the input state. Once the network is fully trained, you can deploy it. For every state 4 Q values would be predicted. You would then choose the maximum Q value and you apply the corresponding action to the agent. For example, if this Q value ends up having the largest number, then the agent would choose this action here, down. Note that this is only one way to implement it. Alternatively, you could have 16 input neurons, each neuron representing a specific state as a binary number. In that case, one of the neurons would be 1 and the other 15 would all be 0. You would still have 4 output neurons though. You need to have a Q value for each action that you take in a given state. This is called Deep Q Network or DQN, and it's a powerful RL algorithm. However, it doesn't work well for us in PID tuning. Let me explain. In the case of vehicle suspension system and PID tuning, we have the following structure. We have a plant. This plant is for a half-car model. It has 8 states. I covered the derivation and control of this system extensively in the course called Vehicle Suspension Control 3, PID plus LQR plus Resonance Analysis. Here, XP and X.B are the car's vertical displacement and velocity respectively. Theta B and Theta.B are the car's pitch and angular velocity respectively. Then XW1 and XW1 dot are the rear wheel's vertical position and velocity values respectively. And finally, XW2 and XW2 dot are the front wheel's vertical position and velocity values respectively. The plant also takes in the control inputs, F sub u and M sub u, which are the forces and moments that actuators in the wheels generate. These control inputs are generated by the two PID controllers, where one is for controlling vertical displacement with these 3 constants, proportional, integral, and derivative respectively, and the other one is for the pitch with these 3 constants, which means that in general we have 6 PID constants that we have to tune, and so the states go into the controller where the relevant error derivatives and their integrals are calculated, and where the PID controllers are applied, and then based on that, the 2 PID controllers generate the control input signal that is applied to the plant. But note that here, the control inputs themselves are not actions in the context of reinforcement learning. Here, the plant, together with the controller, is our environment. And then this box here would be our agent, which is the TD3 reinforcement learning algorithm. And when it's already trained and deployed, then it takes in the states and then it outputs the action vector, which contains these 6 PID constants. This is when your agent is already trained and deployed. However, during training, the environment also needs to send immediate rewards to the tuning algorithm, as you will see later on. The states, they would be the observations. As you can see from this schematic, I'm not trying to have constant PID values. I want to create adaptive neural network-based PID controllers that change the 6 PID constants based on the system's current states. Of course, you could also calculate some average numbers for them. However, the main objective is to have adaptive constants that change in real time based on the states the agent receives. And now, going back to DQN, you would think that if I take this network and then I insert the 8 states that I have here into it from the left side, and then the network would throw out some Q values on the right side, and then I would choose the maximum Q value and the action vector corresponding to it, and that action vector would then be sent to the environment. The problem with this setup is that our action space is continuous. Imagine that your action vector can only have 2 possible values, this one and this one. In other words, all the 6 PID constants can either be 200 or 10, and no other options are available. Then, in principle, you could use DQN to solve this problem, because then your output layer would have 2 neurons, a Q value for the state action pair, where you have this first action, and another Q value for the state action pair, where you have the second action vector. And then you would evaluate these 2 Q values. You would see which one is bigger, and you choose the action accordingly. So let's say that this one is bigger, the first Q, which means that you will choose this action vector, which is this one, and that's the one that will go into the environment, into the PID controller box. The state vector, of course, can have any value. Each element here can vary from -infinity to +infinity, mathematically speaking, but in DQN, the neural net has to return a Q value for every possible action that you can take in a certain state. In the grid world, you could only take 4 actions maximum. No matter in which state you were, you could only take 4 possible actions, and therefore you would have 4 Q values as the output neurons. In this example that we had here with PID constants, no matter your state, you could only have 2 possible action vectors, A1 and A2. So you would only have 2 Q values given by the 2 output neurons. If I created another action vector where 5 of my PID constants would be 10, just like in A2, but the 6th one is 9, then that would be a third possible action vector. In that case, I would have one more Q value corresponding to this action. However, in our case, mathematically speaking, all these 6 constants in the action vector can vary between -infinity and +infinity, even though in the TD3 algorithm they will be constrained to only have values between 0 and 10,000, and it will be achieved with the help of activation functions. However, even when you constrain them like this, since this interval is continuous, all these 6 PID constants, they can have literally any value between 0 and 10,000 because it's continuous. In other words, you can still have infinitely many values for each PID constant. And that means that in DQN, you would need infinitely many output neurons because you would have infinitely many Q values because you can have infinitely many action vectors. And that's of course not possible. That's the reason why Deep Q network would not work in this particular case. We have to do something else to make it work. Let's talk about it in the next video. Thank you.